Hi, Dr. Liang. Dr. Liang?
Yeah, sorry, I'm muting myself.
Okay, it's okay. So should I get started or just wait for a couple of minutes?
Couple of minutes, probably right now. I supposedly we should have more people.
Okay.
Yes,
Okay.
I check everybody who show up. Maybe
Okay.
2 minutes.
Okay. 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 I'll wait for you. If you say start, and then I can get started.
Okay, let's
All right.
yeah. I will check how many people show up. Because
Okay.
some students have not show up yet. Most
Okay.
of the faculty are here now, so.
Yeah, we have more faculty than students.
Exactly. So Chris, I have not seen Chris yet. So.
Yeah, I see my student Andrew is here.
Yeah, Andrew. Yeah, I saw. Yeah. Oh, Dr. Teng is here now, so he's an expert in this area. Okay, should we start now, or I think Dr. Lee?
Yes.
Should we start? It's okay now, or?
Yeah, I think it's okay.
You think it's okay, right? I think yeah, most people are okay. I think okay. Dr. Gao, I think it's your time now. It's your okay. I will leave the podium to you.
Okay. All right. Hi. Good morning, everyone. This is Lan Gao from the Department of Mathematics at UTC. Today, I'm going to talk about logistic regression in R with applications. So I picked this topic because this is related to the project my students who are working on in this for this program. So, and also it's quite widely used in biostatistics area, especially when you analyze the medical data. All right. So I plan to talk about in this way. I know most of the faculty, are here, and probably this is a piece of cake for you. So assuming my majority of audience is students. All right. So if you think that, oh, this is too easy, you can just take a nap. Okay. All right. So I plan to present my talk in this way. So first of all, I would like to talk about the mathematical model of the logistic regression, and then I'll talk about how to conduct logistic regression in R with examples, and most importantly, how to read and interpret the output of the logistic regression in R. And lastly, I would like to show kind of do a showcase of the project of my students have done so far. So, but they are still working on it. So I probably just would like to showcase some of the majority of the findings so far they have got. Okay. All right. So so the real problem is probably most of you know the linear regression, right? So the linear regression, the ordinary linear regression, we assume the response variable, that's the y, is quantitative, it's numerical. But in real life, there are many situations that the response variable is qualitative, it's categorical. For example, now is related to everybody, right? So if you want to use a statistical model to predict the COVID-19, right? Whether people is infected or not infected. So you see this outcome variable is a binary outcome variable, infected versus not infected. And the more commonly in medical field, we would like to use statistical model to predict disease versus low disease, high pressure, no high pressure, right? Those kind of things. So it's very common that the response variable is a binary outcome variable. So usually if we use code, so it's very common to use like a 0, 1, right? 0, 1 represent infected and 1 represent infected and 0 represent non-infected. So later on, you'll say I just use 1 or 0, right? You know what I mean? This is just the two possible outcome of the binary outcome variable. And what the logistic regression for? So usually we would like to predict the probability of an event, how likely that event is going to happen, right? So how likely you're going to get a COVID-19 virus. So this is a probability question, right? So we want to predict probability. You know, the probability is always between 0 to 1. So it's not very easy to directly predict the probability due to the limitation of the range. And on the other side, in the engineering field, especially in the machine learning field, it's quite common to use logistic regression as a classifier. So you want to do the classification. So if you have multiple levels of the categorical variable, so you just predict the labels of the outcome variable. So this belongs to group 1, this belongs to group 2, so on and so forth. So this is a classification problem. So it's also quite common to use logistic regression to classify the outcome variable with multiple levels, right? Or you say class. So the main reason I choose this topic is because it's quite common in biostatistics field and also is common in machine learning field. Okay. So how should we model the relationship of the probability, right, with a set of predictors? So you may notice that here I just write 1x, actually this x represent a set of predictors, not necessarily to be one predictor, okay? So how likely, so here you say I use 1, right? How likely you got COVID-19 infected, so y equals 1. This is a probability question given a set of potential predictors. So we want to do that, right? So now we just leave this for a while. Let's recall for linear regression model how we do that. So this is a mathematical equation for the simple linear regression model with 1 predictor, right? So we can use a linear compilation to predict the outcome variable, right? So here I use p. This p is not a probability. This is a function. More probably I should use y. This is more straightforward, right? So everybody knows this simple linear equation, right? So the graph is a straight line. So beta 0, beta 1 is coefficients. So this is how we model the relationship. So now we want to model the probability. Like I said, due to the range of the probability 0 to 1, it's not very easy to use math equation to model this probability. So instead, we want to use a transformation. Okay, next I'm going to talk about that. So before I give you the official logistical regression model, so let's recall there is a function, it's called logit function, right? So if you have taken the, I think it's calculus, right? The logit function, the graph looks like this. So the range is from infinity, negative infinity to positive infinity, and the function is in this format, log x over 1x, right? So we call this logistic function. Actually, this is the rationale of the logistic regression model. So why we can use this function to do the transformation of the dependent variable y. So keep in mind now, you just need to keep in mind that the curve of this function looks like that, right? So it's not a straight line, and then you see the range of this function is from negative infinity to positive infinity, right? So that's the same for our model. We want the range to be like that, right? Okay, so the logistic function, we actually borrowed the logist function, the logistic regression, we borrowed that function. So we write the logistic function, the logistic regression in this format. So the left side is a function, all right? So now I say this is a function, not the probability, okay? So, and the right side is the exponential function of the lateral e. So to the beta 0 plus beta 1x. So this x is a vector. So now again, not necessary to be one predictor. Later on, you'll see for multivariate logistic regression. So there are a bunch of x here, right? So here for simplification, I just write x here. So we want to fit this equation use maximum likelihood estimation. Recall when we do ordinary regression model, we use least square method, right? So I'm not going to go to the detail of the maximum likelihood estimation, but we just know that this is the method to estimate those betas, right? So we use this method to estimate the betas because essentially we want to predict the model, and we want to find the solutions of the betas, right? And now here comes this. If we go back, if you do some simple algebra, you see we can rewrite this equation 1 to the following format, right? So we can do this, the p of x over 1 minus p of x, and the right side of the equation is very simple now. This is just exponential of a linear combination, right? So we're happy with that because finally we see this. This is what we are familiar with, right? This is a linear combination like the ordinary linear regression model. And then when we do this, you see this range becomes to in this format, because if we define this p of x as a probability function, then the left side, this is the range of this function turns to 0 to positive infinity, right? So this indicates that we have a wider range now. And now, but again, we don't want this is limited to positive numbers, right? So we want to be like the ordinary regression, so that the left side of the equation to be negative infinity to positive infinity, so that we have a more flexible ability to predict this model. So how can we do that? So we want to convert this thing to to something that between negative infinity to positive infinity. So what do? We can take logarithm of the left side. So this turns to this, right? So log of the this whole thing. This whole thing actually, if you recall the curve I just shown you, this whole thing we call logit, right? This is actually in the format of the logit. And there is another name for this we call odds, right? Odds, simply speaking, what odds mean? Recall odds means a probability something is happening over something is not happening. So you see the bottom 1 minus p of x. If I say p of x is the probability you are going to win the game, then 1 minus probability of winning would be the probability that you are going to lose the game, right? So probability of winning over probability of losing. So this is called odds. So you take the logarithm of the odds, then the right side turns to, so recall the last equation, right? So if we go back, you see the last equation, the right side is exponential of the linear combination, right? So now if you take the logarithm, then the exponentiation function is gone, right? It's kind of that you are doing anti-logarithm, right? Anti-logarithm. You are doing, so you take the log, so it's kind of cancel out, right? Logarithm and the exponential, so log of this e, right? So now that's why you say the right side is just a linear combination. Now you say if I use algebra format, so there are a bunch of predictors, right? So if you have k predictors, x1, x2, up to xk, so this is a linear combination of those k predictors. Notice that we have a intercept term. This is pretty much like the way we do ordinary regression, right? You have usually we conclude a intercept term here, that's beta 0, and all the others associated with the predictors. So together you have k plus 1 betas, not just k betas, right? And now we can call the left hand side log odds, right? Log odds, or you say log logit, right? So usually we would like to call log odds, right? Now we don't have to worry about the range of this function anymore, because this thing is between negative infinity to positive infinity, right? So we are happy about that. So when we do prediction, this is a linear combination on the right side. This is what we want, right? We are quite familiar with this linear combination, and the left side is just a function of the function of logarithm of odds. And again, we don't have to worry about the range, because now we can take anything, any real number, right? Okay. Now I would like to because some people, many people may wonder, what's the difference between logistic regression and ordinary linear regression anyway, right? So recall linear regression model. This is a simple linear regression model. Of course, here it's just one variable, right? X. So everybody knows the graph is a straight line. So you see this blue line. So this is the graph of the linear equation, right? Everybody knows that. And now look at the curve. Okay, now this is not, look at the yellow curve. This is the curve of the probability of y equals 1. So this is, so we call logistic model, right? So you see the outcome now is not a linear relationship with your predictors. So this is nonlinear, right? You see this yellow curve is nonlinear. Obviously this is nonlinear. Why is nonlinear? Because if you use math equation to present this y on the y-axis, so this y is this, 1 over 1 plus e to this, right? So this, obviously this is a nonlinear relationship. That's the big difference between the logistic regression and the linear regression, if you use a graph way to show the difference between the outcomes, right? All right, so now you probably have a big picture in your mind. So the logistic regression and the linear regression, right? One is predict a linear relationship. The other is to predict a nonlinear relationship, use transformation of logist function. All right, and also one good thing for the linear regression is that it's very easy to interpret the coefficient, right? So now if you say this linear regression model, so what's this, once you solve those betas, we use least square method to find the solution of those betas, right? Once you have the betas, you can write down the linear equation and you know the specific value of those two betas. And you can easily interpret those betas, right? For example, if you want to interpret the beta associated with X, we say beta 1, right? What this means, this usually in general, we say this is how much change in Y given 1 unit change in X, right? So now if it's positive, that means increase in Y. If it's negative, it's decrease in Y, right? So it's quite straightforward to interpret the betas in this way. But for logistic regression model, this is really a pain to interpret these betas directly. So like my students, some people, oh, I know how to conduct logistic regression in R. It's very simple if I know the code, right? But the most difficult part is how to interpret the outcome. So like here, I mentioned that it's very hard to directly interpret those betas later on. R will give you the betas, all the betas at the same time, but it's quite hard to interpret these betas directly. Okay, later on, I will show you how to interpret those betas using examples, so you may feel much easier to understand. Okay, so now I just want you to pay attention that you cannot directly interpret those betas using the way that we interpret betas of the ordinary linear regression models. All right. Now we already know that how we got these betas. Like I said, we can use maximum likelihood to predict the betas, but here, due to the limited time, I'm not going to go to details how to use maximum likelihood. So I'll skip that. And then also, like I said, when you get the outcome of the logistic regression, the left side is log odds, right? It's log odds. So you may say, I still want to know the probability that the outcome variable equals Y, how likely I got infected of the COVID-19, right? So you want to know the probability. Actually, once you get the log odds, it's quite easy to find the probability. You can simply use this equation, right? You can simply, so this Z means the convolution, right? So that's the beta 0 plus beta 1x and beta 2x, so on and so forth, right? So once you have those betas, you plug into this equation and you can easily get the probability. Also, you can use the R function plot is to find the probability. But usually, if you read the literatures, people would like to use log odds, right? Or odds ratio or confidence interval to interpret the result. So it's not necessary to get the probability all the time. So sometimes when you write an article, you can just get the log odds and then convert to odds ratio. So you may not want to get the probability because people already, the reviewers already know how to interpret the odds, or you say log odds or odds ratio. So those are very confusing concept, but later on I will show you the difference of those things. All right, here I just want to mention that you can also get the probability if you like. All right, then how to conduct logistic regression in R is quite simple. But here I'll just give you a very simple way. Use the general. This is not the variables from the real data yet. Okay, so the function in R to conduct logistic regression is GLM. What is for GLM actually is a function for generalized linear regression model. So logistic regression is just one type of generalized linear regression model, okay? If you take advanced statistics, you may say there are a lot of other generalized linear regression model. Generalized linear regression model is based on ordinary regression model to predict the nonlinear relationship, okay? So if you use a graph way to observe, you observe that there is a nonlinear relationship between your predictors and your outcome variable, you may consider to use general linear regression model instead of ordinary linear regression model because the relationship is not linear at all, okay? So in R, so you just use GLM, and inside, so there are a bunch of arguments inside. So here, let me interpret, let me just explain the most common ones. So here, first of all, you need to, what is this? So this is like if you have used R to conduct ordinary linear regression model, you may be familiar with this. So the left side of this, we call this, this is kind of like a formula, right? So we use this formula syntax to specify the model. So what you want to predict. So here we say we want to predict this guy, Y, right? Y is your dependent variable. So for your specific data later on, you'll see for my example, Y is maybe is stroke, no stroke, the status of stroke patient, right? So, or infected, not infected. It's depending what your real data look like. Okay. So this is your dependent variable Y, right? And then this here, if you want to, what you want to use to predict Y, right? I want to use these three predictors, that's the independent variables, X1, X2, X3. Of course, you may have more than three predictors, or you may just use one of the one, right? If you use one, we call this is univariate logistic regression, right? So this is a more common format. You have multiple predictors, and then the first part is a formula syntax to specify the model, and then you have to tell R your data, right? Specify your data, where these variables from. This is from what data, right? So your data name here, you need to specify your data. And then this thing is very important, family, right? Family equals binomial, link is logic. So now maybe you have some sense of why here is link is logic, because we use logic function transformation, right? And why here is binomial, because you think about the distribution of your dependent variable is because your Y now is a binary outcome variable 0, 1, 0, 1, right? So it's a sequence of 0, 1. So this is we assume is a binomial distribution. So now you say why this is a binomial. This setting is just for logistic regression, which means if you use GLM model to predict the nonlinear relationship, use other for other application, if your Y is not a binary outcome variable, it's just a numerical outcome variable, but is nonlinear with the predictors. You may use other family like Gaussian and Poisson. Okay, so here this binomial thing, this is just for logistic regression, which means this part for logistic regression, you have to set this part, right? And then the first part is very similar to the ordinary multiple linear regression. And then data, of course, you have to specify data. So this is just a very general setting for the logistic regression. So later on, when I conduct the logistic regression, use real data, you'll see we are going to use this kind of code, GLM. Recall for linear regression, we use LM, right? LM. So now this is a generalized linear regression model, GLM. All right. So next, I'm going to show you how to conduct logistic regression using the example data. So this is so I'm going to use the example data from CDC stroke data. So this data is from a bunch of surveys, right? So they just ask many patients across the United States, a bunch of variables and whether they have a stroke, no stroke, all right? So here, our dependent variable, that's the Y, is the status of stroke, right? So we want, some people get stroke and some people didn't get a stroke, right? And then the data set is quite large. The dimension is quite large. It's about 45K of the adult people from age 18 and above, right? And I am still working on this. This data is quite large, and probably starting this fall, I'll ask my student to join me join me to work on this data. So that's why I want to use this data as example. So like I explained, now our Y is status of stroke, right? Stroke, lung stroke, right? So you can code as 0, 1, 0, right? 1, 0, right? 1, 0, right? So what we are going to use, what kind of variables we are going to use to predict this stroke status? So this is very hard to answer, right? So we have a bunch of variables. So we need to explore the potential predictors. So for this presentation, I'm going to just pick some of the predictor. It's not all the predictors. Like I said, we have to explore, right? So in this example, I just choose these variables, right? So I'm going to use the following variables. So one variable is smoke, right? Smoke at least 100 cigarettes or not. So we know smoke is not good, and many literatures shows that smoke is related to the stroke, right? And alcohol drink, right? This is also behavior of the patients. And ever told, so there is another variable is about blood pressure. Ever told blood pressure or not, right? So this is just, so you see this is just, all those is just yes, no, right? Yes, no. And weight in pound, or this one is not, this one is except this one, right? Weight in pound, this is not a yes, no variable. Ever diagnosis with a stroke, so this is actually our Y, right? So I'm going to use all this as X, right? So we have multiple, we have 5X, so 5 predictors. I'm going to show you how to use those 5 predictors to predict the stroke, right? The stroke, that's a dependent variable. And so this is a lot data. You see that I just want to simply show you the dimension of the data set, right? It's quite big. This is a number of rows and a number of columns. This means we have 330 variables in this data. And basically each of the row represents one patient. And before I conduct the logistic regression, one thing I want to mention that, but of course here we are not going to talk about the theorem part due to the limited time. So very important, remember I mentioned a little bit, we assume that those predictors are independent. Independent means they are not related. But in real data, this may not be the case, right? Sometimes they may related, or sometimes they may be highly related. So, but for the mathematical model, the assumption that one of the important assumptions is that we assume the independent variables are independent, which means they should be unrelated, okay? But now let's check, right? Check the real data. So like I mentioned, we want to use those 5 variables. Here, this is a kind of like a 5 by 5 matrix to show you the correlation between those variables. So this is, say, check the correlation between those variables. We assuming they are independent. In statistics, this is so-called multi-collinearity checking. Multi-collinearity checking, okay? So if you take advanced stats, so this is a very important topic, multi-collinearity. We have to do that for multiple linear regression as well, right? Okay, so now I'm going to check the correlation between those 5 variables we are going to use to predict the slope, right? So this figure is by ggplot2. So, but here I'm not going to show you the code, but the code is not a problem. If you use Google, it's easy to get the code, right? So Google is always the best teacher. All right, so here I just want to explain that how to read this kind of figure. So
named Storo. I fight injustice and defend the innocent.
Excuse me, is there any questions? No questions? Okay, I'm going to continue. So here, if you see you see this, right? This on this triangle, this says this is just the relationship between each of the variable with itself. With itself, of course, the correlation is the maximum, right? The maximum. So you see this full circle. That means the correlation is very high. And also you see the scale, right? The correlation, we define the scale from the correlation between -1 to 1. Negative means negative correlated, and positive means positive correlated. And the 1 means the maximum, and -1 means the negative maximum, right? Okay, so also you see the color, red and blue, red or green means a large correlation, right? So you see for the rest of the other like a pairwise correlation, so most of them are just blue ones. Blue one means it's kind of very small relationship or correlation, right? So you see the smallest one is 0, of course, and then 0.2, 0.1, right? And now you see and also the area, that's the pi. The area represents the magnitude of those correlation, right? So you see, actually, after I check this, most of the correlation is between 0.1 to 0.2. So this means none of the variables have none of the 2 variables are strongly correlated. So we don't have to worry about the multi-collinearity issue for now. Okay. So why I mention here, because this is a very, I think this is a must step before you go ahead to conduct a logistic regression, because many people just conduct a logistic regression anyway, right? But I would highly recommend that you check the multi-collinearity issue first. All right, now let's look at the data we are going to use. So this is just a summary, like I said, for those five predictors, 4 of them just yes, no, right? This is white, right? This is white, except the weight in pounds. This is a numerical variable, right? All the others just yes, no. So this is just to show you a very simple summary of all the variables in the data. And Now I'm going to convert the binary outcome to the 0, 1 coded variable, right? Coded variable. So in R, usually we use coded. We need to code the variable if you have a variable like a yes or no. So in general, we just code yes as 1 and 0 as no. But you can do the other way. You can say you can define your own yes, right? So to understand easily, we just use 1 in represent yes. So here you see what I'm doing here is I just want to convert the original yes or no of the stroke status. Yes means the patient has stroke. No means the patient doesn't have a stroke, right? So I just want to convert this to 1 and 0. If yes, that's 1. If it's no, that's 0, right? So this is a very easy thing to do. And then what I'm doing here is probably if for those students who are in the who have taken machine learning, this is very simple to understand. I want to split the data to 2 parts. One is called the training part, training data, and the other is test data. Why I want to split the data to 2 parts? Because I want to use training data to build a model, and I want to use the other part to test the model we will use to predict the stroke of the status of stroke later, right? Because I don't have other data. So I just use the original data as training and the testing part, right? So, but the thing is, how should I split the data? There are many ways to split the data. So here I just use the simple way. Usually we do randomized. So we select a sample randomly from the full data set, right? So here I just select, use the index of the rows to split the data for you to understand easily. Okay, so I use the first row up to 390K. This is for the training part, and then the rest of the data for the test part. So one question you may have is how much should I put in the training set, and how much data should I put in the test set? Usually for a training set, we use 2/3 of the data for the training, right? Probably Dr. Liang knows better than me, and 1/3 for the test part, right? So this is not a very, you know, I have to do that way? No, but it's just for the general rule, we just do that way, right? So 1/3 for the test and 2/3 for the training, right? And then we are ready to conduct logistic regression use GLM function, right? So here I show you, I'm going to show you the first. I just use a univariate model, right? So so you see here GLM. This is the function I just talked about a moment ago, and then the CVDS stroke 3. This is the Y variable is a stroke, right? Is a stroke and not stroke. And now you understand this is a 1 or 0, right? We just code it as 1 or 0, right? And then I want to use smoke 100 cigarettes a day or not. So use this to predict. So you see in this model, I just use 1 predictor, right? Smoke 100. I didn't use all the other predictors I mentioned before. So this is the simplest logistic regression. And then the family, you see here, I say family this, right? Family, this setting is just for a logistic regression. And then you have to specify the data, okay? Now to build the model, I'm going to use the training data, right? I just define the training data, right? And more generally, if you want to use multiple predictors, I use in the training data set, this is the only, this variable is the dependent variable, right? All the others, I want to consider all the others as predictors. So there is a short way to write this. So because the name, there are a long list of the names, so I'm not going to write down all the names here. Instead, I just put you see, I put a dot here, right? What this for? This means, okay, in the training data set, okay, take this one out as the dependent variable y and treat all the others as predictors. So that means, okay, if I write this way, means all the others are going to be our predictors x, right? So remember we have 5x now, including the smoke, right? So the second model, then I store the result. I store the result. I give the name of the result, right? The univariate model. I save this result as model.u, and then the multivariate model, I save this as model. And the next, I'm going to use interpret the output of the model, not the univariate model, because this is more general, okay? So I'm going to use the result of this model, right? Because this is more common. Okay, now this is the result. Okay, if you want to see the details, all the details of the result, you can just use a simple code summary, right? Summary what? Summary of the result of your model. Remember, I just store the result of the multivariate model as MODEL, model. Okay, now I want to look at the result. What does the result look like? I just do summary model, right? And then this is the first part, right? This is just show you, okay, you are using this model, right? So this indicates you are using all the other 5 variables in the training data set. And then the second part is the divariance of the residuals. So usually this part is useful to check the goodness fit of the model. Okay, so here I'm not going to go to the details, but we can talk a little bit later. Okay, we are going to focus on this part. Right? That's the coefficients. So that's the betas. Remember, our model is, we assume the model, right? So the model is this log, right? Probability that stroke versus 1 minus stroke, that's long stroke, right? Probability of long stroke equals, okay, beta 0 and beta 1, x1 is this guy, blood pressure, right? And ever have told high pressure or not, right? So you know what I mean? So beta 3x, that's, you just, okay, look at the list of the variables here. And now we have 5x, right? So 5, sorry, 5, right? So now R found those coefficient numbers, which means, okay, now your beta 0 is the intercept, right? So you can see here is negative 3.2. And then what is your beta 1? Beta 1 is the coefficient associated with blood pressure, right? So that's x1, so 1.3 something, and the coefficient x3 is negative 0.56. Okay, so on and so forth. So all those are betas, right? Are betas. So you can easily find those betas. Now remember, we need to interpret this. What these numbers tell you anyway, right? So can you explain those numbers, those coefficients? So we conduct a logistic regression, multiple logistic regression easily, but how to interpret this result? And also, you may have heard that p-values, right? So each of those coefficient number is associated with p-value. And all those p-values are highly significant because they are less than any significance level here, right? Anyway, it's less than the most conservative significant level, 0.001, right? So, which means those, so simply speaking, those predictors can significantly predict probability of stroke. In other words, you may say those predictors are significantly related to stroke, right? Status of stroke. So that's what we want to know, right? That's what we want to know. But how to interpret those relationships in details? For example, if I change, I increase the weight, right? Increase the weight. If people have a greater weight, should the probability of stroke is higher or lower, right? How to interpret those things. So that's what I want to do next. Remember those betas is just the original coefficient. That's the beta to predict the left side. This is log odds, right? Is the log odds. So it's not easy to interpret those betas in log odds. So what we can do? We can do this. Okay, so we want to anti-logarithm. So we just do, we can do exponentiate each of those numbers here, right? See, if we do, because if you want to interpret those betas, you have say, okay, if I increase the for example, the x3 by 1 pound, and how much change in the log odds, right? But if you interpret that way, people would still get confused. What log odds anyway, right? So to avoid that kind of thing, we want to exponentiate each of the coefficient number. See why we do that? If you exponentiate each of this, then you can, if you keep the others the same, you see it's kind of, you are getting rid of this log, right? So the left side is just odds. Odds is easier, right? To understand, odds is easier, right? Okay, so we can easily do that in R. You just do the, you can simply do exponentiate of the coefficient number, okay? And now we get this table. You see that the difference between this table and the previous coefficient number here is, if you say here, for example, I pick one, okay? I pick the one number, the second one, the blood pressure. Okay, if I pick this number, 1.30, 1.305, now this turns to this number, right? Where this number from? This is the original number. You do the e to the original number, which is 1.305, right? So check this out. So this is how these numbers come from. So you do anti-logarithm, right? So after you get these numbers, we call those number odds ratio. So if you read the literature, whenever the paper use the logistic regression, this is quite common. This is a very kind of like a very standard statistic you have to report, odds ratio. So now tell me what this 3.69 mean, right? So I know the odds ratio is 3.69, but how to interpret that? So this is a quite large number if we use 1 as a reference. So this is larger than 1. Simply speaking, if odds ratio, okay, sorry. If odds ratio larger than 1, this indicates a higher risk. Okay. If odds ratio equals 1, that means equal risk. If odds ratio less than 1, that means a lower risk. Okay, this is a very general explaining, right? So odds ratio allow you say, okay, this number obviously 3.69 is larger than 1. This means higher risk. Higher risk than what, right? Now you see this, yes, right? You see her automatically put this yes. This means, what this means? This means a patient with a higher blood pressure. Yes, right? Yes. Have you ever got a higher blood pressure? Have you ever, if you go to the the annual physical checkup, have you ever been told high blood pressure? Yes. Yes means those patients have a higher risk of getting a stroke, right? So that's what you mean. But you still you still didn't explain the exact value 3.69 yet. So how to interpret this? This means, so you can interpret this as when those people with high blood pressure had the risk of stroke is 3.69 times, or you say the odds ratio, the odds, okay. I shouldn't say risk, because if it's risk, then we have to calculate in another formula, okay. We can say the odds is 3.69 times of the patient without high blood pressure, okay. So odds is 3.69 times, okay, odds, okay. Now you get rid of the log, remember, so this is easier to explain. Odds is higher if you say people get the stroke, the odds of people get stroke is higher. That means the probability of people get stroke is higher, right? But we cannot say the probability of people get a stroke is 3.69 times of probability, okay? So this is very important. You cannot, odds doesn't mean, odds is not the same thing as probability. Probability means, okay, probability of y equals 1, right? Odds, what odds mean? Odds means probability that y equals 1 over probability y is not equal to 1, right? So you see they are different, okay? So here I just don't want you to misinterpret this number as probability. This is odds. Odds higher means risk higher, but this doesn't mean the risk or probability is 3.69. You can only explain the odds is 3.69 times of the other group, okay? So this is the interpretation, and how to check the fitness of the model. You can use ANOVA, right? ANOVA and the name of the logistic regression. So remember we store this as a model. So if so here you can say check the d-variance numbers. Higher number, that means this is this predictor contribute to the model more than the others. So now we can simply check those. So you see the weight here is only 33.2, and the average drink is 19.2. This two contribute to the model less than the others. However, the probabilities, right? The p-values shows that they are still significant. So that's why we still put all the put these two into the multivariate logistic regression model, right? So this is how you check the goodness phase, and then we can also access how good this model is, right? We can use one study. We can also use the other criterion. So here I just simply use the accuracy. So how likely, so remember we have a test data, right? So you can use the test data to check how good how accurate your model is. So here I use the test data, right? So you use the test data, and it turns out the accuracy is 96, around 96%, right? This is good enough, right? Accuracy is 96%. You know, the largest testing kit of the COVID-19, the false positive is probably is up to 5% or to 10%, right? So this is, if you have accuracy 96%, I think this is good enough. And also you can use the ROC curve to check how good your model is, right? So ideally we would like the area equal to 1, right? But now obviously this area, the area under this blue curve is not equal to 1. The area, the larger the better, right? The larger the better. Now we have this area, 0.722. Of course, this is less than 1, right? Less than 1. Again, we think that this is good enough, right? All right. And lastly, I would like to quickly showcase the findings of my students have done so far, but this is from another project. But it is still related to logistic regression. But in that project, we use Cox regression. Cox regression, slightly different from logistic regression because the outcome variable is time related, right? So we want to use a model to predict the likelihood of people who get injured during sports. Okay, in the data set, we have all different kind of sports, right? And here, this is the other PI is from the Department of Health and Human Performance at UTC, and these are all my students. And Andrew is here. I know Chris is here. No. Okay, Jenny. I know Jenny is working. And then this Tweety, she just graduated in May, and yeah, she did a very significant contribution to this project. So here, the research question is we want to use we want to investigate a bunch of risk factors of injury and build a statistical model to predict the risk of injury among athletes in all those kind of sports. So here is some of the players, you know, before they enroll to this program, they already had injuries before, okay? So this is a distribution of the total injury and the retrospective injuries and the prospective injuries. And then this, we found out that gender is probably a significant factor of the injury. And basically speaking, we found that females is more likely to get injured during the sports, okay? And also the other factor could be sport type, right? There is all different kinds like a basketball, soccer ball, softball, and then tennis, volleyball, and cross country. So cross country, you know, is by common sense, you say is less likely to get injured than football, right? So yeah, this makes sense too. So you see here, we found out that soccer ball is that's the red curve, right? Most of the time, this curve is above all the others. So that means this the probability of getting injured for football player is higher than all the other sports. Okay, and this is to show that if the player has a previous injury and is more likely to get a second injury. Okay, so if you have a injury before you enroll the program, so it's more likely you get get a second or the third injury. And then this is the summary of this is a summary of the players between stratified by gender, so males and females, and this is all those kind of sports and the BMI. Okay. And then this lastly, this is just the information of the R Studio. So if you want to know what kind of version I'm using, so if you want to play this data again, you want to repeat my my codes. So you have to make sure we have the same version. Otherwise, due to randomization, so the result may be slightly different. Okay, so and then that's all for my presentation. Thank you all for your attending this meeting. I'm happy to take any questions if you have.
Thank you.
Dr. Teng, I think I will give you the opportunity for the first the question. You have a question, Dr. Okay, just any questions? Okay, I have the free question, Dr. Gao, as a matter of fact. The first question is for the students. I think there's a student ask, can you just post the slides on the, yeah, first it's very good presentation. Yeah, very good. And the student asked, can you post your slides on some just like the Google Drive or student so that they can download?
Absolutely, I would be happy to do so. I'm going to send you my slides to you, and you can share with all the because I don't know how many people would like to access. You can just share or put it in the same folder as the other stuff like a survey and YouTube
Okay.
links.
So
yeah.
I can get a green light from you, right?
Okay, yeah, I'm going to send you this file to you, and you can just put it in the Google documents.
How about the code? Is the code?
The code. The code is actually is because I use R Markdown in RStudio, so the code is integrated with the slides. So if I will provide you two versions. This version is a PDF version. That's you kind of lead out the R Markdown file, and I also will give you the R Markdown file. In that way, student can see the original source code.
I see. Wow, that's nice.
Thank
okay,
you.
now I will ask her to go to my question now. The question one is the calculation of the beta coefficient. There's many just the optimization method we can get the beta 1, 2, 3. So, but in your just in the R, just I think similarly we have no choice, right?
In R, default is to use maximum likelihood method.
Okay.
If you want to use other method, yes, you can specify. But for logistic regression, commonly we use maximum likelihood method. Like when you do ordinary regression model, you can use least square method.
Yes. Yeah.
You can also choose the other method like a maximum likelihood. You can specify the method in R easily.
Okay, so the default.
Yeah, that's a very good question. Yes, you can do that way.
I see. Okay. So my second question is about your data set. Is like the data set is smoke 100.
Yeah.
Smoke 100 is not a continuous data. Like from what I learned is like
not continuous. It's just a yes or no. It's basically ask you, do you smoke 100 cigarettes per month?
Mm-hmm.
I think it's per month. Yes, it should be. Okay, let me go back to the code. The key for the variables is right here. I think. Oh, sorry. Yes, here. Yeah. Do you smoke at least 100 cigarettes? I think this cannot be one day, right? It should be per month. Yeah. If I remember correctly. Yeah, this should be, if it's one day, that would be a lot. Yeah, so it's a yes, no, it's a yes, no variable. Yeah, it's a binary variable.
So in this, for this example, you can put like the predictor. You can put like a quantitative predictor and then just the categorical, just the data together.
Yes, absolutely. When you consider a set of predictors, those predictors can be categorical variables, can be numerical variables. So for example, age, right? Age. Sometimes people may think age could be a numerical variable, so we can treat it as a numerical variable in the model. Yes, logistic regression, if you want to treat age as a numerical variable, that's fine. Also, you may want to redefine this age to like groups. So for example, I may want to define this age as okay, under 65, and the other group is larger than 65. So now you say you kind of convert a numerical variable to a categorical variable. That's also okay. So to answer your question, absolutely, you can include any kind of variables, either numerical variable or categorical variable.
I see. Okay, thank you. Yeah.
Thank you.
Thank you
Very
for
good.
your question.
Great thought, yes.
This is Meirong speaking. I
Huh?
think this is
Yes.
Meirong speaking. Hi.
Hi.
Thank you for the presentation. It's a lot. Information is very helpful. I just have two quick questions. One quick question actually, because like I don't know much about R, but in social science, sometimes we would need to check, the interaction effects, right?
Yes.
For
Yes.
example, how age, I mean, like say for example, how gender and smoke
Yeah.
has interaction effects on the dependent variable, or sometimes we would look at like clustering effects, right? For example, the clustering effect, for example, the patients that belong to one doctor, doctors belong to clinic, sometimes we collect data as clusters. So I just wonder, in this case, I believe R has, code to deal with this. I just wonder, how do we find those?
Okay. Okay. Very good question. Actually, interaction effect actually is very, very common. Here, for our example, I didn't consider interaction effect because I assume I don't want to get too complicated. Actually, R can easily conduct a model with interaction effect. So remember, in my model, I just list all the possible predictors here, right? So if you have x1 and then x2 and x3, actually, if I want to, for example, I want to consider the interaction effect between x1 and x2, I can easily put here in R x1, x2. This looks like x1 times x2, but actually this means this doesn't mean really multiplication. This just mean the interaction between x1 and x2. Yeah, this is it's very easy to do in R.
Okay, I think it's similar as we do it in SAS. We do the same thing.
Yes. Yeah, the syntax is quite similar to SAS. SAS, I know. Yeah, you also do. You can do like in this format x. Looks like a multiplication actually means interaction in SAS, and also SPSS. I'm not familiar with SPS, but I know there is a way to specify the interaction terms in all those statistical languages.
Yeah, thank you so much.
Thank you. I think you also asked another question. Can you repeat?
Yeah, it's a clustering effect. Like for example, suppose these patients are from different neighborhoods, right?
Yes.
But in social science, we examine neighborhoods impact on people's health. So then you have the people in one household and household in different neighborhoods and neighborhoods in different cities, and the overall the city's policy or for example, healthcare policy will have impact on this patient's well-being as well, health outcome as well. So sometimes when we collect data like clusters, when we analyze them, sometimes we take consideration into such data, data collection. I just wonder.
Okay. Yes, actually, you ask a very, very, very good question. I would say this is, I remember I had this kind of situation when I worked with a professor from Department for Biology, and they also collect data from different area. And for that, what we can do is we can treat the, for example, different area data as a random
effect.
Yes, random effect.
Okay.
So actually in R, we can also, R can handle random effect. But for that, we need to modify the ordinary logistic regression here. We use mixed regression model. So mixed means you have fixed factors, or you say fixed effect, and then you have random effect as well. So that's kind of, so you can use a mixed.
Thank you. I think like R is,
yeah.
Thank you. I think syntax is to a lot of extent is similar to SAS.
Yeah, R is a language that is very easy to learn for beginners. But the drawback is that if you don't use for a while, it's also easy to forget.
Yeah. Thank you so much. This is very helpful.
All right, thank you for your question.
Good morning. Oh, sorry. Good morning.
Hi.
I have a question. My name is Desohe Irabor. I was on RStudio and I tried downloading ggplot on RStudio. I have the most recent version of RStudio, but I was not able to do it. R mentioned something about not being compatible with ggplot. This version of R not being compatible with ggplot. Do you have any suggestion for that?
I would usually for that kind of question is due to the version of the R. So two suggestions: you may want to upgrade your RStudio.
Yeah, so the RStudio version that I have is the latest.
Okay,
yeah.
Then you upgrade. You need to upgrade your R because this kind of R use RStudio as a platform. But when you actually conduct those code, that's in R, right? So try. I think the latest version. Notice that you know at the end of my you can easily check the R version you are using right now by using the code. So here, yeah, you see here I use the R version 4.02. I believe this, yeah, this version is just released in June.
Yeah, so I have that version.
You have
that's
that
the version? Yeah, because I just opened R and I'm looking at it. So that's the version I have. And it's it has the same date as yours as well.
Okay, then can you try to install ggplot2?
Yeah,
ggplot2 is a kind of updated version of the original ggplot.
Okay, okay.
Yeah,
I did see that.
So here you see all the figures in my graph here. In the presentation, I use package ggplot2. So this is, I would recommend that you, you go ahead to install this package.
Okay, I've got it. I found it.
Okay.
Thank you.
All right. Thank you for your question.
This is Norman, and can you hear me?
Yes.
Yes, in Python, when we do logistic regression, we can do grid search to optimize the hyper parameters to avoid overfitting. Is this the same in R or something like that? Can you speak about that?
Oh, yes. Yes, very good question. So his question is sometimes you may worry about the overfitting issue. So if that happens if you have too many predictors in your model and your data set is relatively small. Here, I'm not worried about my overfitting issue. I didn't even mention that because I have a huge data set, like a 450K. So yes, if you have a small data set, you need to make sure you cannot contain too many variables in your model. So too many parameters, or you say too many predictors. So there is an ad hoc rule. So if your if I use P represent your number of parameters and N represent the dimension of your data, the sample size. So usually your P should less than 10% of your sample size. So otherwise you may have an overfitting issue. Also, most likely the overfitting issue is due to the multicollinear issue. So it's like the way I check the collinearity before I actually conduct the logistic regression. So I think that could be the case of the overfitting as well. So to answer your question for overfitting issue, data sample size, and then the multicollinearity issue, you have to check those two.
Thank you.
All right, thank you.
Quick question to follow up on what he asked. What exactly counts as a small sample size in which we would have to fear overfitting?
Okay, so yeah, actually there is no universal question answer for that. So how large is the sample size large enough? So when you collect the data, so I know when I do the statistics consulting with a Lan Gao hospital here, so usually there are many times they would ask me to do a sample size and a power analysis before they actually collect the data.
Okay.
So I would, if you do that before you collect the data, you wouldn't worry about the sample size. So you need to do consult with a statistician or yourself. You I know there's a lot of web-based software allows you to calculate the minimal sample size you need for your study. So if you do that before you collect the data, then you shouldn't worry about that. But if you say, hey, here's what I have, this is a data set I have, I cannot get more, that would be an issue. So usually if you do, you may only need to, you may only report descriptive stats. You cannot report in inferential statistics report, because your conclusion cannot, your conclusion could be very misleading due to the small sample size. And to answer your question, how large the data set should be large enough? So like I just explained, your parameters should be less than 10% of your sample size. If your sample size, if you say you have like 20, you have 20 parameters, but you only have 100 patients in your data set, I would say the sample size is too small.
Okay, so that's if the parameters are...
Yeah, the number of parameters.
Okay, number of parameters.
Yeah, this is not a serial, okay? So it's just
Yes.
like a ad hoc.
It's like an
tool.
idea.
Yeah,
Okay.
yes.
Okay. Thank you very much.
Thank you. Is there any other questions?
Dr. Gao, this is Meryl again.
Hi.
Hi, I didn't follow with that. I know I did the sample size calculation in Power Star G. There's a software on that. But you mentioned the numbers parameters. Could you mind repeat that sentence, please?
Oh, yeah. So are you talking? Yeah, I usually I would recommend. So if I talk to the doctors in hospital, I would like ask them how many patients in your data set and how many parameters they would like to predict their outcome variable. So that doesn't mean that when you collect the data, doesn't mean that you cannot collect more variables. You can collect as many variables you like.
Yeah.
But when you use statistical model to predict, use predictor model to predict your outcome variables, you cannot consider too many variables in your model. So generally speaking, we say the number of parameters in your model, so should be less than 10%, okay? Should be less than 10% of your sample size N. So this is a very general rule. If you have, otherwise you may have a overfitting issue. Whether it's really overfitted or not, you can use, good need fit models like ANOVA I just did there to check whether there is an overfitting issue or not. That makes sense?
Yeah, it makes sense. I mean, because in the past they use a lot of secondary.
Yeah, don't get me wrong. I mean, when you collect the data, you can always collect as many as you want. But when you consider to use predictor model, you cannot contain too many variables in your model if you have a small sample.
Yeah, I think in the past they used a lot of secondary data set, so you wouldn't worry about the sample size problem. And when you for your own data, this is a tricky question sometimes can be.
Yeah, yes.
Thank you.
All right, thank you. Any other questions? Dr. Liang. Dr. Liang.
Yes, I'm here.
Okay. All right. Can we
Yes.
call the end of this meeting?
Yes. Thank you, Dr. Gao. Very great. I think from the feedback, you did a great job. Yeah, very just impressive. Everybody, please, particularly the students. I'm going to post the Dr. Gao's talk on the YouTube, and also the survey. Please complete the survey. Yeah, ASAP. So, and I'm going to post the slides and then the YouTube as well. So encourage you guys can encourage your friends to to watch it. Yeah.
Will the video from last week also be on the same channel?
It's different. It's YouTube, but it's different channel.
Okay.
Other than I think I will put that in the same channel.
Okay.
I'm going to broadcast the channel, so you are not going to miss it. So.
Okay. Thank you.
Mm-hmm. Yeah. Thank you for. Yeah.
Okay. Thank you, Dr. Liang. Okay, I'm going to end this meeting. So.
Okay. Thank you, everyone.
Thank you.
See you guys next week.
Bye-bye.
Thank you. Bye.
Bye.
Bye.